So let's imagine we've got these two general vectors. Let's say vector A, which has a magnitude of 124 meters and is at an angle of 15 degrees up from the x-axis. So I've drawn A here, 125 meters long and 15 degrees up from the x-axis. And then another vector B, which is 50 meters long and at an angle of 25 degrees up from the x-axis. So here's B, 25 degrees up and a magnitude of 50 meters. So here, two general displacements that you might have made going for a walk or something like that. And the question is, what is the sum of these two vectors? What is A plus B? Well, let's call it vector C. And what would vector C look like on our diagram here? It would be a vector that goes from the tail of A to the head of B. So it's going to look something like this. And I'll try and draw this. There we go. As accurately as possible. So there's the vector C. Well, we can see what it looks like graphically from this diagram, but it would be nice if we could figure out how to describe C quantitatively. Can we figure out what's the magnitude of C? What's the angle between C and the x-axis? Something like that. How are we going to figure that out? Well, last time we actually figured out the magnitude and direction when we added the two vectors, because those vectors happened to be perpendicular, and we could use the two sides, the perpendicular sides, to figure out the magnitude of the hypotenuse in that case. If we could figure out what the components of C were, in other words, if we could figure out this length, which, like before, we would call C sub x, the x component of C, and this side, which would be C sub y, the y component of C. If we could figure out Cx and Cy, we could figure out what the magnitude and direction of C are, just like we did in the previous problem before when we had the two perpendicular displacements. Well, how can we find Cx and Cy? Well, if we notice, let's look at A. A, we could figure out, or if we could figure out, what's the x component of A, and then what is the x component of B, what do we notice? The x component of C is exactly equal to the x component of A plus the x component of B, so that we have that AX plus BX equals CX. The sum of the x components of A and B give us the x component of C. Likewise, the y component of A and the y component of B add together to give us the the y component of C. Here's AY, BY, and CY. So that we have AY plus BY equals CY. So we could actually figure out the magnitude and direction of C by first figuring out the components of C, and we find the components of C by adding the components of A and B, x components added together, y components added together. So can we find the x components of A and B? Well, yeah, that's like the previous problem, but just worked in reverse. Before, we had x and y, the x and y components, and we put it together to find the net displacement. In this case, we've got the individual total displacement, and we're going to break it down into components. So what are AX, AY, BX, and BY? Well, got some room over here. Let's look at AX and AY. So we've got a triangle that looks like this. The length of this is A, which is 124 meters. And this is 15 degrees. This is AX, and this is AY. What is the cosine of 15 degrees? Cosine, if you remember, and hopefully you remember your trigonometric identities, cosine is adjacent over hypotenuse. In other words, it's the adjacent side, which will be AX, over the hypotenuse, A. In other words, multiplying by A, AX equals A cosine 15 degrees, or 124 meters cos 15 degrees. I'm actually going to typically skip this step, and I'm going to go right to the x component is the hypotenuse times the cosine of the angle, as long as the angle is given in terms of the x-axis, how far it is from the x-axis. If you give the angle in terms of the y-axis, the sine and the cosines will be reversed. But for this one, x component is hypotenuse cosine 15 degrees. Likewise, AY will be hypotenuse, 124 meters, times sine of 15 degrees. And from B here, we've got the hypotenuse is 50 meters and the angle is 25. We're going to get something very similar. We'll find that BX equals 50 meters cosine 25 degrees, and BY is 50 meters sine 25 degrees. So what are those values? Well, I happen to have them right here. AX is 120 meters. AY is 32.1 meters. BX is 45.3 meters. And BY is 21.1 meters. There we go. So we can now come back over here and put these in. So AX is 120. BX is 45.3. That's 45. And that'll be CX. And AY is 32.1 plus BY, which is 21.1. And that's going to be CY, which leaves us with CX is 165 meters. CY is 53.2 meters. There we go. We've done it. We've figured out the components of C, CX and CY. Now we can put those back together and figure out what the magnitude and direction of C are. Okay, I'm going to erase this and redraw C. Using these components for C, I've redrawn C here. CX is 165 meters, CY 53.2 meters, so we end up with C that looks like this. We could draw this as a vector if we wanted, like this. There's C. We know that the magnitude, because this is a right triangle now, C squared magnitude is equal to 165 meters squared plus 53.2 meters squared. Multiplying this out, take the square root, we have C is equal to 173 meters. At a direction of theta, tangent of theta equals 53.2 meters over 165 meters, opposite over adjacent, which is 0.322, and then theta is the inverse tangent of that, which gives us 17.9 degrees. So we have two different ways that we can describe C. We can describe it with its magnitude and direction. C equals 173 meters at an angle of 17.9 degrees above the x-axis. Or we can describe it in terms of its components. C, that's C vector, is equal to 165 meters x hat plus 53.2 meters y hat. Great. We have a very, very general way of adding vectors. And again, we could have more than just two. This could be A plus B plus C plus D plus E, whatever, equals F. The x component of F would be AX plus BX plus CX plus DX plus EX, or added as many as we have. And then the y component of the sum, F sub y, would be AY plus BY plus CY plus DY plus EY, added up as many as we want. And if in general this was in 3 dimensions, we would have the z component of the sum, F sub z, would be AZ plus BZ plus CZ plus DZ plus EZ, as many as we had. So this is very, very easily extended to 3 dimensions. All we have to do is just add in a third component, CZ, or whatever the vector is, and we would introduce a third unit vector, z hat, which is sometimes called k or k hat. You might have seen I, j, and k. Well, I'm going to write it as x hat, y hat, and z hat. All right, very, very good. Now, so far, all the vectors that we have been looking at have been in the first quadrant. In other words, all of these vectors are pointing to the right and up. To the right, in other words, with a, or let me just say that for now. To the right and upwards. What if we have vectors pointing in other directions? What happens to those? What kind of components do they have? Well, let's take a quick look. All of the vectors we have been looking at have been in the first quadrant, as I just said. In other words, pointing to the right and up. And we have found then that the x components have always been positive. The y components have also been positive. What if we have vectors pointing in other quadrants or along an axis or something like that? Then what happens? All right, let's take a look. If we have a vector b in the second quadrant, then it's pointing to the left and up. Its x component would be negative, but its y component would be positive. If we have a vector in the third quadrant, its x component, cx, would be negative, and cy would be negative. In other words, it's pointing left and down. A vector in the fourth quadrant, say d, in this case dx would be positive, but dx would be negative. In other words, it's pointing to the right and down. Keep in mind, it does not matter where these vectors are. I've drawn all of these as though they were starting from the origin, but remember, all that matters is that two vectors are parallel with the same magnitude, and then they're the same vector. So A could be here, it could be over here, and still have positive x and y components. It could be down here, and still have a positive x and y component. In other words, even if the vector is down here, you think, oh, well, it's in the third quadrant, but it's pointing as though it were in the first quadrant, and that's what's important in terms of its components. It's still pointing to the right and up, so it would still have a positive x component and a positive y component to describe the direction of the vector. Both of those would still be positive. So it doesn't matter where the vector is, what's the direction? You can always, if it's easier for you, think about bringing the origin back down here, and then how would you describe it there? Well, then it's obviously in the first quadrant, positive x, positive y. Very good. Now, what if we've got something kind of in between? What if we had a vector that was right along the x-axis? Call this vector e. Well, in this case, e sub x would be positive, e sub y would be... Now, the signs of the components are exactly the same as if you had a point in the quadrant. What would the components of a point be on the x-axis? It would be a positive x, and e sub y would be 0. Not positive or negative, it's actually equal to 0. A vector along here, call this vector f. In this case, f sub x would be 0, f sub y would be positive. A vector over here, call this vector g. In this case, g sub x would be negative, g sub y would be 0. And a vector right along this axis here, call this vector h. In this case, h sub x would be 0, h sub y would be negative. Okay, there we go. And then likewise, you can imagine what they would be if you included the z-axis as well. Very good. For all of these vectors, actually, the z component would be 0. If they are in the xy plane, the z component would be 0. All right, very, very good. So that allows us to describe any two-dimensional vector that we want in the x and y plane. Very, very good. We've talked about adding vectors. How about subtracting vectors? How would we subtract vectors? So imagine we have, say, a vector A and a vector B. We know how to add them. We put them head to tail. So if we were to add A and B, we would take B, put it up here, and then the sum of A plus B would be a vector that went from here to here. That's the way to add them. What about subtracting them? How do we take, let's say, A minus B? Well, I would imagine that we would agree that that should be the same as A plus negative B. A minus B, it seems reasonable, should be the same as A plus negative B. So what is negative B? What is the negative of a vector? Well, if we had a vector B and we added the negative of it, what do you think we should get? If you take a number and add its negative, what do you get? Well, we would expect that that should give us 0. In terms of vector addition, what would that mean? If you had no displacement, what does that mean? It means you end up back where you started. You're exactly where you started. So if I have a vector b, here's a vector b, what would I add to b? What would I add to the vector b in order to get 0, or in order to get back where I started? Well, if I start here and go here, to get back to where I started, I would start here and go back here. That, we would expect, should be negative b. In other words, it is a vector, negative b is a vector with the same magnitude as b, but in the opposite direction. So negative b is a vector with the same magnitude as b in the opposite direction. Now, this actually comes back to that point where I was talking about what if we take a scalar and multiply by a vector, and I said, well, what if a is negative? Well, what would we get if a were negative 1? If a were negative 1, we'd get negative v. In other words, we'd get a vector with the same magnitude, in other words, 1 times v, but in the opposite direction. So when we multiply by a vector by a negative scalar, we end up again with a vector with a magnitude that's equal to the absolute value of the scalar times the magnitude v, but in the opposite direction. So what we can say is then that the magnitude of this vector, remember we can put absolute value signs on the vector to make the magnitude. This will be the absolute value of a, so whether a is positive or negative, this will give us a positive times the magnitude of v. So that will work for positive or negative scalars. If it's a positive scalar, the vector that we get, if a is positive, this vector will point in the same direction as v. If it's negative, this vector will point in the opposite direction as v. Okay, so good. That kind of clears up one little exception that we had mentioned before. Now here, let's remember that negative b is a vector with the same magnitude as b, but points in the opposite direction. So, how do we add, or how do we subtract? We add the opposite of b. In other words, over here, what's negative b? So, negative b will be the same magnitude as b, but in the opposite direction, which would look like that. So, something like that. And then we add that to a. So we bring this over here, like that, and the vector then that goes from the tail of a to the tip of negative b is the vector a minus b. Well, you can imagine that that is the same direction as going from the tip of b to the tip of a, like this. So a minus b is a vector, if you put them tail to tail, would be a vector that goes from the tip of the second vector, tip of b, to the tip of a. Or you could just think of it as finding negative b and then adding negative b to a and going from the tail of a to the tip of negative b. All right, very, very good. What we are going to do next time, is see how we can take these ideas of our two-dimensional vectors and how will they apply to an actual two-dimensional kinematics problem. We looked at some examples of motion in one dimension and how we describe the position and velocity, acceleration, things like that. How can we apply these ideas that we've derived for vectors in 2 dimensions to an actual problem, a kinematics problem in 2 dimensions? We'll start that next time.